All right, we're going to get started here. Welcome back, everyone. I'm pleased to introduce our first speaker of this Cold Regions Engineering session, Dr. Bruce Williams. Dr. Williams is a research scientist at CanMet Materials, studying material issues related to energy in the transportation and nuclear sectors. His research focuses on deformation and fracture of metal alloys. He uses a combination of computational, experimental, and statistical methods in his work. Welcome, Bruce.
Thank you. So today I would just like to talk about our material model for TC128B. We saw a presentation yesterday on this, and this kind of expands on that. We'll be particularly talking about the low temperature material model and its application in full-scale finite element analysis. And why do we want to use a full-scale finite element analysis? That's to model impact events. Very expensive to do this experimentally, and particularly at the low temperature. So what I'll be talking about is I'll be comparing the response at a room temperature, 23 degrees Celsius and minus 40 degrees Celsius. We do a lot of laboratory scale testing in the laboratory, and then its application in the large scale FE, in this case of hard coupling impact. We learned about the Charpy V-Notch test that's often used to understand the material at low temperatures and dynamic strain rates, about 100 strain per second. That is at the upper limit of what we would expect in a crash event. So this is just let me put on the pointer here. So what we see on the left here is the response between minus 40 degrees Celsius and the room temperature. And so if you take the area under the curve as the energy absorbed, you absorb much more energy at 24 degrees Celsius. What we're interested in at low temperatures is this sudden load drop. The material transitions from a ductile crack to a brittle crack, and with that you get a sudden load drop in the material. So we want to make sure we can capture that. The image on the right is at the quasi-static rates, very slow strain rates, and we compare dynamic and quasi-static, and what we can see is that there's a difference in the energy absorption between the two strain rates. And so we would just want to be able to capture this in our material model. This is the stress strain curve, true stress strain curve. The blue is minus 40 degrees Celsius. The gray is the room temperature. And we can see that decreases in temperature increase the strength of the material. And there's differences between the dynamic and quasi-static strain rates as well. And we all need to capture this in the model. So image models have become a popular way of capturing the failure response of materials, and most commercial finite element codes will have these damage models in. I won't go into it other than to say it takes a lot of testing. If you take a section from the tank car, they're small scale specimens. You have to do a lot of tests, a lot of simulation and optimization methods in order to come up with these material models. And they're often valid for one temperature and one strain rate. In our case, we're interested in multiple temperatures and multiple strain rates. And so we expanded the models that were available in literature. Using just limited data from like tensile and Charpy tests, we were able to match the Charpy response of the material. So for instance, we can get a little bit of ductile growth, crack growth, and then suddenly we get this load drop due to the brittle crack. And that's particularly what we wanted to capture in the models, in the material model. And this was about a year ago that we did this. So in the current work, we did a little bit more testing to further validate our material model at minus 40 degrees Celsius. And we use these types of laboratory specimens with notches in them. And the reason that we're using notches is because that's the type of geometry that we might expect to be present in a crash. And so when we test these materials at the lower temperature, it gives us load displacement data that we can compare our FE predictions to see how well it agrees. If I just compare the minus 40 degree response with the 24 degrees response, what I see is the minus 40 degrees response, which is blue, actually absorbs slightly more energy than the room temperature response. In all of the quasi-static tests that we performed at minus 40 degrees Celsius, we did not see the brittle fracture with a sudden load drop. And that was a bit unexpected. We were expecting to see that sudden drop, but we didn't. At low temperature, minus 40, at these quasi-static strain rates, we can absorb just as much, if not more energy than at higher rates. So just this next slide just presents a couple images here of the FE analysis. The key takeaway point from this slide is that these is a very fine mesh. The mesh size here is 0.2 millimeters. When we go to large scale FE, that is too small for a large scale. So we have to take that into account, and I'll explain that a bit later on our slides. So the key takeaway is it's a very small mesh size that we do in the laboratory. This next slide here just compares some of our predicted FE simulation predictions compared to the experimental data. The colored red and blue is the FE predictions, black and gray are the experiments. And the key point here is that we're capturing the response fairly well. Both this low displacement response of the material and the point at which the cracks initiate and the material fails. So the next step is, now that we have confidence in our material model, we can model the full-scale, large-scale FEA. And in this case, we're modeling a tank car hard coupling event. And we're modeling it at speeds up to 10 kilometers per hour. So not as fast as maybe a full-scale crash, but it is an impact event. We're particularly interested in the hard coupling where the sill and the subsill attach to the tank car. And so that's where we're analyzing the strains in this region down here. There's a lot of work that was done experimentally at room temperature by the FRA. They have a lot of experimental results from these large-scale experiments, and the strain plot here shows that we can capture that response pretty well. The strain rates here, if we take the slope of these curves, that would give us the strain rates. The strain rates are pretty small. They're much less than 100 strain per second. They're closer to that maybe 0.1 strain per second. But we just wanted to make sure that we can capture that in the models. And so just a little bit about if we include the meshes here. I mentioned that 0.2 millimeters is far too small for a full-scale FE model. And so we actually used a submodeling technique to capture what happens. We often start off with a 10 millimeter element size in the sill and the subsill regions. And then we can go down, if we see a stress concentration, we can remesh it with, say, a mesh size of 2 millimeters, and then we can better predict what happens in that location. And if when we get damage and crack initiation, we can even go down to the 0.2 millimeters. And so we go from a fairly global mesh size down to a local region. Long story short, with the hard coupling is we didn't see any damage initiation because at the 10 kilometers per hour. The strains were pretty small and it just did not initiate any damage or crack initiation in the material. In order to get cracks or maybe damage initiation, we expect that you have to have a flaw in this region. I should note that we did not use a weld material model in this work. It's a little bit different, but we wouldn't really expect to see damage with a weld model anyway, unless we had a crack present in the weld regions. And so that is a little bit of recommendation for future work is to model a flaw in these regions. And the same, this was at room temperature, also the same at minus 40 degrees Celsius. We just did not have aggressive crash conditions to cause damage in the predictions without a flaw or crack present. And I think that was just a summary of the work. So the main key takeaway that we saw from the work was at minus 40 degrees Celsius, stress concentrations, quasi-static. We did not see the brittle failure, the cleavage fracture that we might have expected to see at cracks and at higher strain rates. In generally, our material model can match well with the experiments, and so we can start studying more aggressive impact conditions. I'd just like to acknowledge our collaborators are at CanMet Materials, in addition to our partners at Transport Canada. So, thank you.
Perfect. Thank you, Dr. Williams. The discretization that you guys are able to obtain in those models is very impressive. If there is time for questions, if anyone wants to ask one, we'll give it a minute here before we move on. So there is one from Matt Heron. Are there plans for weld analysis?
I think that was the recommendation coming out of this work, is that we need to model the weld, and particularly the material behavior of the weld that my colleague Jonathan discussed a bit yesterday. And so we do have plans to do that, but that is basically the next recommendation coming from this work.
Perfect. Well, doesn't seem to be another question, so we're going to move on to the next presenter. Thank you so much, Dr. Williams.
Thank you.